Hello friends and welcome at my channel. Today we're talking about the chain rule of differentiation. I'm going to prove it, show you why it's important to use it maybe, and we'll do some applications as well. You see daylight, I managed to do it during the day, which is nice, so let's go for it. Okay, imagine we have f of x equal to the square root out of x squared plus 1. And we would like to compute its derivative. So this function is defined everywhere. The domain is all the real numbers. We don't care about some steep positions or whatever. The radicand, so the value under the square root, is never 0. So we have basically no troubles about this expression. So using the basic principle, we are having, first principle, we're having limit h towards 0. We're having square root out of xo plus h and squared plus 1 minus the square root out of xo squared plus 1 divided over h. The next step is we are repeating it, what we're having. I have to just maybe write it a little bit more compact. I'll do my best. So we have it like this. I just repeat what we had previously, and then we multiply times 1. And this one we can write the way we like it, and I'd like the square roots to move away. So what I'm doing is I'm having basically the same what I previously had, but we're adding now, okay, in order to get to binomial formula. Surprise, surprise. Which is not. We've done it so many times already. I think you're familiar to this one. All right, so there you go. Now we have the limit h towards 0 still. So what do we have here? Well, in the numerator, the square roots are gone, okay? So we have xo squared plus 2xo h plus h squared plus 1 minus xo squared minus 1 divided over h times, parenthesis opened, xo plus h squared plus 1 plus square root out of xo squared plus 1, close it. Then, see what's happening. 1 minus 1, xo squared minus x squared, xo squared, everything is gone. So we really have only those expressions in the numerator where we can take h using the distributive law backwards outside of the parentheses. So we're going to have 2xo plus h, and then we divide it by h times the parentheses. This is what we're doing, okay? And now we can easily cancel the h values. We are having the limit here, h towards 0, 2xo plus h divided over the square root out of xo plus h squared plus 1 plus square root out of xo squared plus 1. So as you can see, I'm having no troubles with h anymore in the denominator, because I had the trouble here as h was a factor, which we canceled. Now it's not a factor anymore, so basically we can let h to be 0. So if this one is becoming 0 and this one is becoming 0 as well, we're going to have 2xo in the numerator and twice the same square root in the denominator, which means we're having 2 times xo squared plus 1. We can cancel it, so the outcome is xo divided over the square root out of xo squared plus 1. That's the result. All right, so like you can say, okay, it's a nice function. Okay, we can produce its derivative. And we need kind of trick with binomial formulas and blah, blah. And maybe we're not always able to find the trick, or we don't see it immediately, or it's going to take so long. So maybe what you can see is that our function is consisting kind of few layers, okay? We have few functions like put together. So our function f of x being equal to square root of x squared plus 1 consists of t of x, which is the parabola x squared plus 1, and it also consists of k of x, which is square root out of x. So we can show that k of t of x is exactly our function, which means we have k of x squared plus 1, because t of x was x squared plus 1, and now we are taking square root out of x squared plus 1. So that's the story. So check. Our assumption was correct. Make sure you understand that if you change the order, it won't be right. Okay? K of t of x, let me show that to you, is fine, but t of k of x wouldn't be fine. It would be t of, what is k of x, is square root of x. What does t do with x? Well, it brings it to square, and then it's adding 1. So square root of x squared plus 1, it's just x plus 1, okay? They are not equal. So the idea is, could we try to produce a derivative out of such a, let's say, a chain of functions? Is it possible? And the answer is yes. So let me remind you that we have basic principle with h-method, but we had also one more idea how to write down the derivative with the so-called x-method. So have it this way. This is also the derivative at xo. We're going to need it in a few moments. All right. So let's assume we have two differentiable functions, and we're basically proving the chain rule of differentiation. So what is the assumption? The assumption is our function f of x consists of two differentiable functions, which are k and t of x, and they're together differentiable. This is important. If you remember, bad boys, I'll link it here, are the only trouble we could have, otherwise everything's cool. And, well, let's write down what we have. F prime at xo is the limit h towards 0. Well, we have f of xo plus h minus f of xo divided over h. That's fine. We're having a limit h towards 0. So what is f of x? As you can see, this is k of t of x. So this is k of t of xo plus h minus k of t of xo divided over h. I'm just using the definition. But we can multiply times 1. It's kind of trick again what we have to use here. And this one we're writing this time as t of xo plus h minus t of xo divided over t of xo plus h minus t of xo. Now we're having a product of two fractions, so that means we're multiplying numerators and denominators, and we can also rearrange them because of the commutative law the way we like it. Okay? So if I have, for example, a divided by b times c divided by d, I'm having a times c divided over b times d, and I could, for example, keep the numerators the way that I have them, but I have to rearrange the denominators, so I'm having a divided by d times c divided by b. So I'm doing exactly the same here. I'm having k of t of xo plus h minus k of t of xo divided over, now I'll bring this guy right here, so it's t of xo plus h minus t of xo multiply times, let's put it, t of xo plus h still minus t of xo divided over h. We switched the denominators, like I told you here. So now we have a limit of a product, and if you remember from our last video, we can only separate the product in limit if we can make sure that the new two limits do really exist. So do we know it here? No, we don't, but let us see what's happening. So first of all, we have the first limit, k of t of xo plus h minus k of t of xo divided over t of xo plus h minus t of xo, that's fine, times limit h towards 0, t of xo plus h minus t of xo divided over h. Can we do it? Well, we don't know yet. That's why we still have this question mark right here, but We know that the functions are differentiable, and you see this is exactly t prime of xo, which is nice. What about the first one? Well, it looks a bit more complicated, but let us see what's going on. So once again, f prime at xo was the h-method, the first principle. This is f of xo plus h minus f of xo divided over h. Everything's cool. But also, it was a limit x towards xo, f of x minus f of xo divided over x minus xo, right? And now see what's happening. Well, if we look at this limit, and maybe we do one pre-move, as we do it in chess, if we consider limit h towards 0 of t of xo plus h, and we know that the value of t of xo does exist, then we can easily put h equal to 0, and the result is t of xo. So we have no troubles to run h towards 0. So basically, it looks maybe a bit awkward now if I do it for the first time, and you haven't seen it here, but I'm not changing anything. Instead of writing h towards 0, I'm just writing t of xo plus h is running towards t of xo, of t of xo plus h. And this is equal to t of xo. You see that? So what I'm saying here, h is disappearing. H value is disappearing. And these are two equivalent expressions, so I'm not changing anything. So basically what we're doing, we're just rewriting it here, and instead of writing h towards 0, we're just writing t of xo plus h is running towards t of xo, which implies that h is disappearing. We still have k of t of xo plus h minus k of t of xo divided over t of xo plus h minus t of xo, yeah, well, and then times literally t prime of xo, which does exist because the function was explained as a differentiable, right? So it was the prerequisite. Okay, now what do we have here? Well, if you look at the x method of computing the derivative, you will see we have the difference between those two values, and the first value is running against the second. Now, look carefully. Do we have the same here? Yes, we do. This minus that, and we have exactly the left value approaching the right one. Well, what a coincidence. Well, it's more than that. F of x minus f of xo we have in the numerator. K of this kind of x minus k of xo in the numerator again, and the derivative value that we have is at xo. So the derivative value that we have of k is at t of xo. So we really have the x method here, truly. Just pause the video, compare the right-hand side with the left-hand side, and see it's exactly the same. There's nothing which is kind of going differently or something. It's really exactly the same, but the derivative was at xo of f. Now, this is the derivative of k at t of xo. That's it. So what we have is k prime at t of xo times t prime at xo. Okay, so the inner derivative times the outer derivative. Maybe you kind of memorize it at school, at high school, at college, at university. Don't do it, please. Okay? We need 15 minutes to prove it, but now you have it forever. Let us see whether it's working in our example. If we're talking about f of x being equal to square root out of x squared plus 1, we said t of x was the parabola, and k of x was the square root. So, and we know already that the derivative here was x divided over square root out of x squared plus 1. We just proved it, right? There you go. That's the result. Now, f prime here would be, now look, this is very important. We need t prime, and we also need k prime. So we need k prime at t of x, and we need t prime of x. Make sure you understand it's k prime at t of x, not just k prime. Let me show you the difference. What is t prime of x? T prime of x is just 2x. What is k prime of x? K prime of x is 1 divided by 2 square root of x. But this is not what we need. And you see, if you memorize, you just don't get it. Because what we need, and that's why we proved it, it's k prime at t of x. So what I need to do now, I take k prime of x, and instead of putting x inside, I'm putting t of x. What is t of x? It's x squared plus 1. So this is what I need. And I get 1 divided over 2 square root of x squared plus 1. Because instead of x, here, I'm putting x squared plus 1. You got it? Perfect. So what we have is 1 divided over 2 square root of x squared plus 1 times 2x. Boom, boom, bam, bam. And what we have is x divided over square root of x squared plus 1. Way easier to compute in this case. And gladly, we do have the same result. Which proves it's nice. Okay, let me do one more example maybe. So if we have f of x equals to e to the power of sine of x, what's going on here? Well, we have two functions, once again. Maybe at the beginning, where you are right now, make sure you write it down. Take your time, take 2 minutes. It won't hurt you, but it will help you to avoid many mistakes at the beginning. Then you're going to get smoother, you're going to get quicker, you can skip those steps. But at the beginning, I highly recommend not to do this. So t of x, the inner function, is sine of x, and k of x is e to the power of x. Can I check it? Yes, I can. F of x would be k of t of x. Is it working? Yes, it is working. We have k of sine of x, and sine of x is being put into the power of e, which is e to the power of sine of x. So check. Don't have to do the check, but you have to maybe do the separation. So what we need is t prime of x. Sine is the cosine. I haven't done the video yet, but I'm gonna make it. And once I've done it, I'm gonna link it here. So we kind of see in the future together. And if you see the link now. And k prime, this is e to the power of x, but we need k prime of t of x. Now you see why I'm so focusing your attention at this point. And we're having e to the power of sine of x. So the total derivative would be e to the power of sine of x times the cosine of x. Okay? Thanks for watching, guys. See you in the next video. I hope you learned something new. Stay tuned. Mathematics is beautiful and life as well. See you. All the best. Bye-bye.